Hello everyone, I'm Dr. Rizwana, working as a professor of physics in Institute of Aeronautical Engineering. So in my previous video, we were discussing about electron in a periodic potential, Bloch's theorem, and also we have discussed about Kronig-Penney model. So in Kronig-Penney model, we have seen that electron, when it is moving in a periodic potential, then what happens? It will give rise to allowed energy bands and forbidden energy bands. Okay, so now we'll move further and we'll see how this band theory is going to help us in order to differentiate solids into conductors, semiconductors and insulators. So in our last video, we have discussed about this plot. Okay, so we have seen our Kronig-Penney model. In Kronig-Penney model, we have seen that when we have electron moving in a periodic potential, then that potential is varying with periodicity, and how that potential, it will give rise to potential wells and potential boxes. Okay, so here we have our potential well, and in this potential well, our potential of electron is 0, and these are our potential barriers whose height is V0. And here we have considered two regions. When your electron is between in the potential well, when it is between 0 to A, its potential is 0, and when it is near the potential barrier, its potential is V0. Then what we have done here is, and we got this very important equation by applying this, what we have done, motion of electron in such periodic potential, we have taken Schrodinger's wave equation and we have applied solution by taking into consideration the Bloch's theorem. So we end up having this very important equation. And what is our P? P, it is given as mV0 AB by H cross square, and this is called as potential barrier strength. Very important point. Now we are going to see how this potential barrier strength is going to make an electron free or bond. So role played by this potential barrier strength. And we have seen that because right hand side of this equation is bonded between +1 and -1, our left hand side should also be bonded between +1 and -1. Okay, so here we have plotted a graph by taking alpha A on x-axis and left hand side of this equation on the y-axis. Okay, and here alpha is variable. We have substituted different values of alpha, and from this graph we got permitted values of alpha and unpermitted values of alpha. So these are the shaded regions, allowed energy regions, which are formed by permitted values of alpha. What are the permitted values of alpha? These are those values of alpha for which left hand side of this equation it falls between +1 and -1. And what are unpermitted values of alpha? These are those values of alpha for which left hand side of this equation it will go beyond either +1 or -1. So those permitted values of alpha, because alpha is proportional to energy, so it is given by 2me by h cross square. So E is equal to alpha square h cross square by 2m. So when we are getting permitted values of alpha, you will get permitted values of energy. So these shaded regions formed by permitted values of alpha give rise to allowed energy bands. What do you mean by allowed energy band? Electron can move only with those energies. So we are showing those waveform only in those shaded regions, and these are forbidden energy regions, which are formed by unpermitted values of alpha. These are those values of alpha for which left hand side of this equation is going beyond either +1 or -1. So already we have discussed these 4 conclusions. Now we are going to discuss in detail about this potential barrier strength. What happens when P goes to 0 and what happens when P tends to infinity. So here we are going to discuss about P versus energy relation. Now first, I'll take my P tending to infinity. What happens if P goes to infinity? When P goes to infinity, now we have our equation. What is our equation? P by alpha A sin alpha A plus cos alpha A is equal to cos K. We have this equation. Okay. Now P, what happens if P tends to infinity? When P tends to infinity, this whole terms become infinity. And if this whole terms becomes infinity, okay, so infinity plus cos, it has to be between +1 and -1. So this whole left hand side will become infinity. How is it possible to have cos? Right hand side again we have cos. How is it possible to have cos to be infinity? So it is possible only if I take my alpha A or sine alpha A to be 0. If I take my sine alpha A to be 0, then this term will become 0. Okay. So we have this term becoming 0. Then I can define value for this cos. So the only solution, if I take p tends to infinity, only solution possible for this fourth equation. What is our fourth equation? P by alpha A sine alpha A plus cos alpha A is equal to cos K. So only solution for this equation is I have to take sine alpha A to be 0. What do you mean by sine alpha A 0? For which values of alpha A, sine alpha A will be equal to 0? Alpha A is equal to plus or minus n pi. For these values of alpha A, our sine alpha A is becoming 0, where n is a positive integer. Okay. Now from this, what is our alpha? Alpha, it comes out to be n pi by A. What is A? A is our interionic spacing. But we know alpha, we know this alpha. So now what I'm doing now, I'm squaring here. So here I'm squaring this term. I'll get alpha square is equal to n square pi square by a square. Okay, we'll get this. But what is our alpha square? Alpha square is 2me by h cross square is equal to n square pi square by a square. And we have our h cross as h by 2 pi. If I substitute h cross as h by 2 pi, and if I rearrange the term, then I end up having my energy to be n square h square by 8ma square. So what is this expression? This expression is for energy associated with particle in one-dimensional box. Particle in one-dimensional box. And for particle in one-dimensional box, it will have discrete energy levels. What do you mean by discrete energy levels? Only certain particular values of energies are allowed. Not all energies are allowed, but only certain particular values of energies are allowed, and these energies are allowed. And these energies are allowed for values of n is equal to 1, n is equal to 2, n is equal to 3. You are going to have E1, E2 and E3. This is our discrete nature. Okay, but band theory, it has given rise to energy bands. So, but when we are taking P to be infinity, we are saying the discrete energy levels. So, what is happening here? If we see this figure, now as P is increasing, when potential barrier strength is increasing, when barrier strength is increasing, then what will happen? When it is becoming infinity, what will happen? Electron is restricted to stay in that potential box. So, electron, it is restricted to stay in this potential box. It cannot come out. So, it will act as a bound electron. And when it has bound electron, it will have only restricted energy levels. Only it will have discrete energy levels. Discrete energy levels means they are represented by lines like this. It means that what is happening to width of allowed energy band, it is decreasing. Let P tends to infinity. Instead of having band spectrum, we'll have line spectrum. So when P tends to infinity, when potential barrier strength is infinity, what happens? Width of allowed energy band decreases, and instead of having bands, continuous allowed energy levels, we'll have discrete energy level. Only certain particular values of energies are allowed. So it means that our electron is becoming a bond electron. So it is giving tight binding limit to electron. Okay, now what happens when there is no potential barrier strength? There is no potential barrier. So here we have this. So I think this is our figure when our P tends to infinity. Again, if I plot alpha A against left hand side of this equation. So instead of band spectrum, I'll have line spectrum. Now when P tends to 0. So what do you mean by P tends to 0? So it means that our V0 is equal to 0. There is no barrier. So when there is no barrier, then electron can move freely anywhere. Okay. So if I substitute P tends to 0 in our equation 4, okay, P by alpha A sine alpha A plus cos alpha A is equal to cos K. If I substitute P to be 0, then this term will become 0. Here I'll have cos alpha A to be cos K A. So we'll get this cos alpha is equal to cos K. From this alpha is equal to K. And what is our alpha? Alpha square is equal to 2me by h cross square. And what is our K? K is equal to 2 pi by lambda. And I'm substituting our matter wave equation h by mv. And what is our h cross? H cross is equal to h by 2 pi. So if I substitute all this here, okay, after this I'm going to make alpha square is equal to k square, and in place of alpha square and k square, if I substitute, I end up having E as half mv square. So if I simplify it further, I'll have my energy as half m. So we'll have our energy as half mv square. So here still I need to substitute k to be 2 pi by lambda, h cross to be h by 2 pi. So if we solve it, our energy comes out to be half mv square. E comes from our Schrodinger's wave equation, and in Schrodinger's wave equation, E is total energy, and usually total energy is combination of potential energy and kinetic energy, but here potential energy is 0. What do you mean by potential energy being 0? It means that there is no barrier, okay, and your electron is a free electron. So there is no, as you can see, there is no shaded region and unshaded region. We are showing waveform everywhere. It means that electron is free to move toward the crystal. So this will give rise to free electron limit. Okay. So here when P tends to infinity, we'll get bond electron where we have strong potential barriers which will stop motion of electron. Whereas if potential barrier strength is 0, then electron is free to move. So this gives rise to free electron theory. This is in accordance with the free electron theory, which is our classical theory. Okay. So we have seen here when electron will behave as like when free electron and when it will behave as bond electron. And based on this potential barrier strength, our solids, they are going to be conductors, insulators and semiconductors. So next we are going to discuss about the classification, but before that we have to discuss about different types of energy bands and what is the origin of energy band formation. Now we got energy bands. We have seen that when we have plotted alpha A versus left hand side of our equation, we got energy bands, allowed energy bands and forbidden energy bands. And what you have to observe here is, so energy bands concept comes only if we take energy bands. Energy bands concept comes if we consider entire solid as a whole. I have to consider entire solid as a whole. Whereas energy level concept comes if you consider single atom. That you have to understand. So when you are considering whole solid as a whole, you will have this concept of energy band. And what is a band? Band is set of continuous or closely spaced energy levels. So set of closely spaced energy levels. And when I'll have such set of closely spaced levels, when more atoms are brought together. Now see here, when we take an isolated atom, what will happen? Electrons are tightly bonded. That attraction between the nucleus and electron will be very strong. So your electron cannot come out. So that's why we'll have only energy levels. But when we bring more atoms, which occurs in case of the solids, what will happen now? Electrons will start moving from one place to other place. Then you will have intermixing of their energy levels. So we will have intermixing of their valence electrons, you will have intermixing of their energy levels. And when your intermixing of energy levels takes place, then there is a possibility to form set of closely spaced energy levels. And that set of closely spaced energy levels gives rise to continuous band, and that band is nothing but energy band. So how this band comes? It comes because of overlapping of electrons of adjacent atoms, and that bandwidth will be largest for outermost atomic electrons. So here we are trying to show when two electrons come together, what happens when n number of electrons comes, then we'll have n number of closely spaced energy levels. So here in this case, discrete energy levels are far away. But when we have more atoms coming very close to each other, because of intermixing of their valence electrons, intermixing of energy levels takes place. Now energy levels, they'll come very close to each other, and this will give rise to energy band. So energy band concept comes when we consider entire solid as a whole. Okay, so now how many types of energy bands we have? I think already we know about this representation. Till now we were discussing about allowed energy band and forbidden energy band. There are two types of allowed energy bands. What are those two types of allowed energy band? Valence band and conduction band. And this valence band and conduction band, they are separated by forbidden band. This is also called as energy gap. Okay, what is valence band? So valence band, it consists of series of energy levels that are occupied by valence electrons. It means that whatever electrons are there in valence band, they are without energy. They don't take part in conduction. Whereas if you supply energy to these electrons in the valence band, then what happens to these electrons? These electrons, they'll jump across the forbidden band and they'll go to conduction band. Okay, now what will happen here? Hole will be created. And here this electrons in conduction band, they'll take part in conduction. So there is a possibility for electron to have energy or to stay in valence band or conduction band. And that region which is separating these valence band and conduction band, it is called as forbidden energy band. Electron can never exist in forbidden energy band. And for electron to, like immobile electron to become mobile electron, it has to get this much of energy equal to energy gap. If it is able to get that energy, suppose if this EV is topmost of valence band, EC is bottom of conduction band, what is our energy gap? EC minus EV. If you are able to supply this much of energy to electron in valence band, then it will become mobile and it will take part in conduction. And different properties of solids can be considered by taking this energy band diagram. So here we have three bands. Of course, two are allowed energy bands, which are valence band and conduction band. When your electron in valence band, it won't take part in conduction. When electron is in conduction band, it will take part in conduction. Now, based on this band theory, now we will be able to explain why we have this classification of materials as conductors, semiconductors and insulators. So now comes the important conclusion of our band theory. So band theory, what is the main important significance of band theory? It is able to explain why solids are classified as conductors, semiconductors and insulators. And on what basis we have this classification? This classification, it is based on width of forbidden energy gap. So based on this classification, it is based on width of width of forbidden energy gap, we have these three types: insulators, semiconductors and conductors. Now insulators. So what are insulators? Now here we are talking about these insulators. Now insulators, forbidden energy gap is very wide. So this gap is very, very wide. Okay, so it means that for electron in valence band, to make it a conduction electron, to make it go to conduction band, I have to supply large amount of energy. And what happens if I supply that much of energy? Our material will get spoiled, it will get damaged. Okay, so I cannot make conduction electron, I cannot supply that much of energy. Now why? Why is it so? Why its forbidden gap is very large? Why it is large? Because if you take insulators, in insulators, electrons are very strongly bound to nucleus. So when electrons are very strongly bound to nucleus, then they cannot come from their attraction and they cannot jump from valence band to conduction band. Actually, they'll have more number of valence electrons. So they have completely filled a valence band. And in insulators, our conduction band is empty. Always valence band, either it is partially filled or completely filled. And conduction band, either it has to be empty or partially filled. So in case of insulators, valence band is completely filled. It means that it will have more number of valence electrons. And when valence electrons are more, they are more very much attracted to nucleus. So easily they cannot come out. We have to supply more amount of energy. That is nothing but having forbidden gap very wide. So obviously, because there are no free electrons, the resistivity will be high and they are bad conductors of electricity. And to name few insulators, you can go for glass, plastic, rubber. So rubber we have, then plastic. So these are some of the examples of insulators. Okay. Then coming to semiconductors. Now if you go to semiconductors, as you can see, width of forbidden energy gap, sorry, this is not one. So if you consider the semiconductors, width of forbidden energy gap is small. Compared to insulators, it is very small. It means that energy required to make mobile electron is small. If I supply small amount of energy, easily they'll take part in conduction. So here if you take in semiconductors, what is the band gap? See, in case of insulators, band gap, it is around 10 electron volts. So very high amount of energy. Whereas in case of semiconductors, as you can see, that band gap is 0.7 electrons in case of germanium, 1.1 electrons in case of silicon. It means that I need small energy in order to make electron go from valence band to conduction band. At first, at T is equal to 0 kelvins, there are no electrons in conduction band. But as temperature increases, they'll gain energy and they'll jump from valence band to conduction band. Here they'll have resistivity, and here actually these are insulators at normal temperature, but when we increase temperature, they'll act as conductors. Why? Because forbidden energy gap is very small, they'll take energy and they'll jump to conduction band. And of course, we know famous examples for semiconductors. We have silicon and germanium. Then what are conductors? Best example for conductors, metals. If we consider metals, now see here there is no forbidden energy gap at all. It means that in order to make electron take part in conduction, I don't have to supply energy. Without any energy also, electrons will be freely moving. They will be freely flowing from valence band to conduction band. There is no barrier at all. Your valence band and conduction band will be overlapping each other. There is no forbidden gap. Okay, and there are plenty of electrons available for conduction. They have very high conductivity and very low resistivity. So just without any energy also, free electrons, they'll come out of their atoms and they'll move freely and they'll give rise to very high conductivity. So this we can explain using this. So completely based on that forbidden energy gap, we can have these three types of materials. So here successfully our band theory, it is able to explain our main classification, why different solids will have different behaviors based on their electronic structure, why some are insulators which does not contain any free electrons, why some are semiconductors which will take properties of both conductors and insulators, and which consists of two types of charge carriers, electrons and holes. And whereas if you take conductors, why they have very high conductivity. So all these concepts are better explained using this band theory. So with this, I'll come to end. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.